Welcome to this comprehensive mathematics lecture on statistics, designed specifically for Class 10 students. Statistics is the powerful science of collecting, organizing, analyzing, and interpreting numerical data to make sense of the world around us. In our modern data-driven society, everything from sports statistics and financial markets to health demographics and weather forecasting relies on the mathematical principles we will study today. Historically, the word statistics originates from the Latin term status, meaning state, as early governments utilized data collections for taxation, census planning, and agricultural management. Today, we will transition from simple ungrouped data sets, which we learned in earlier classes, to more complex grouped frequency distributions. We will master the three central measures of tendency: mean, median, and mode, using direct, assumed mean, and step deviation methods. Let us begin our analytical journey. In daily life, we often encounter raw data that is scattered and unorganized. While ungrouped data is useful for small sample sizes, large data sets become unmanageable unless we group them into classes. Grouped data is organized into class intervals, such as 0 to 10, 10 to 20, and so on, along with their respective frequencies. The frequency represents the number of times data points fall within each class interval. To analyze group data, we define the class mark or midpoint, which is the average of the upper and lower limits of a class. The class mark serves as the representative value for all data points within that class interval. We also define the class size, or width, as the difference between the upper limit and the lower limit. In Class 10, we focus on continuous class intervals, ensuring that the upper limit of one class matches the lower limit of the next class, preventing any gaps in our distribution. The arithmetic mean represents the average value of the dataset. For group data, the direct method assumes that all observations in a class interval are concentrated at its class mark, denoted as xi. If fi is the frequency of the ith class, then the product fi times xi represents the total sum of observations in that class. To find the overall mean, denoted as x bar, we sum these products across all classes and divide by the total number of observations, which is the sum of all frequencies, fi. The formula is written as x bar equals the summation of fi xi divided by the summation of fi. The direct method is straightforward and highly efficient when class marks and frequencies are small, single-digit or double-digit numbers, allowing rapid manual calculations. When the numerical values of the class marks and frequencies are large, calculating the product fi times xi can become tedious and prone to calculation errors. To simplify this, we introduce the assumed mean method. We choose a convenient class mark near the middle of our distribution as our assumed mean, denoted by the letter A. We then calculate the deviation, d1, of each class mark from this assumed mean, where d1 equals xi minus A. Since deviations are much smaller numbers than class marks, multiplying fi times d1 is significantly easier. The mean, x bar, is then calculated as the assumed mean, A, plus the sum of fi d1 divided by the sum of fi. By shifting the origin to A, we keep calculations compact and reduce the chances of mathematical errors. If the deviations, d1, still consist of large values, and all class intervals have an equal width or class size, denoted as h, we can simplify our calculations even further. This is the step deviation method. We divide each deviation d1 by the class size h to obtain a scale-reduced variable, ui, defined as xi minus a, divided by h. These values of ui typically simplify to tiny consecutive integers like -2, -1, 0, 1, and 2. The product fi times ui is extremely easy to compute. The final mean, x bar, is calculated as the assumed mean, a, plus the class size h, times the ratio of the summation of fi ui to the summation of fi. This method is the ultimate calculator shortcut for large group datasets. The second measure of central tendency is the mode. In ungrouped data, the mode is simply the observation that occurs with the highest frequency. However, in a grouped frequency distribution, we cannot determine the exact mode by inspection alone. Instead, we identify the class interval that has the maximum frequency, which we define as the modal class. The actual mode of the distribution must lie inside this modal class. To avoid complex curves and mathematical ambiguity, we assume that the distribution is unimodal. We calculate the precise mode algebraically using the frequencies of the modal class, the class preceding it, and the class succeeding it. This algebraic interpolation method allows us to locate the peak frequency point within the modal interval. Let us examine the mathematical formula for calculating the mode of group data. The formula is written as mode equals L plus the quantity f1 minus f0 divided by 2 f1 minus f0 minus f2, all multiplied by the class size h. Here, L represents the lower limit of our modal class. The variable f1 is the frequency of the modal class itself, while f0 is the frequency of the preceding class, and f2 is the frequency of the succeeding class. The term h represents the class size. The difference f1 minus f0 measures how fast the frequency climbs on the left side of the peak, while 2f1 minus f2 scales this difference relative to the total drop on both sides, ensuring that the mode is pulled closer to the neighbor with the larger frequency. The third measure of central tendency is the median, which represents the middlemost value of the distribution when all observations are arranged in order. For group data, finding the middle value requires us to calculate the cumulative frequency. The cumulative frequency of a class is the sum of frequencies of that class and all preceding classes. If n represents the total number of observations, which is the sum of all frequencies, then the middle observation corresponds to the value of n over 2. The class interval whose cumulative frequency is equal to or just greater than n over 2 is defined as our median class. The median value lies within this class. The cumulative frequency table serves as our running total, tracking the growth of our data population class by class. To compute the median of group data, we use the algebraic interpolation formula. Median equals L plus the quantity n over 2 minus Cf divided by f, all multiplied by the class size h. Let us break down each parameter. The variable L is the lower limit of the median class. The term n is the total number of observations. The variable Cf represents the cumulative frequency of the class preceding the median class, which represents the number of observations already counted before entering the median class. The variable f is the actual frequency of the median class itself, representing the density of observations within that interval, and h is the class size. This formula linearly interpolates the remaining observations needed to reach n over 2 across the width of the median class. Now that we have mastered mean, median, and mode, it is vital to understand when to use each measure. The mean is the mathematical average and is highly sensitive to extreme outlier values, which can skew the result. The median is the spatial middle point, representing a robust measure that is completely unaffected by outliers, making it ideal for skewed distributions like household incomes. The mode is the most common value, useful for business decisions such as determining which shoe size to manufacture in the largest quantities. In Class 10, we focus on unimodal distributions where there is a single clear peak. Bimodal distributions, which contain two separate peak frequencies, are avoided at this level to ensure that our algebraic formulas remain mathematically valid and unambiguous. For moderately skewed distributions, there is a fascinating empirical relationship connecting our three measures of central tendency. Discovered by statisticians, this relationship states that 3 times the median is equal to the mode plus 2 times the mean. This equation, known as the empirical formula, is extremely useful. If you know any two measures for a distribution, you can easily calculate the third measure without needing the raw frequency table. Let us summarize our key takeaways. Mean represents the balance point, median represents the middle coordinate division, and mode represents the peak density. Together, these three measures provide a complete, multidimensional view of any group dataset in statistics. Thank you for attending this Class 10 Mathematics lecture on statistics. We hope you have built a clear, intuitive understanding of mean, median, mode, and their group calculation methods. If this video helped you visualize data patterns and equations, please subscribe to our learning channel, hit the like button, and share it with your classmates. Don't forget to click the notification bell so you never miss an academic update. Keep practicing, keep analyzing the numbers, and we will see you in the next mathematics lecture.